Okay, so the first thing we are going to start with, obviously this is going to be falling within the parts of supervised learning, but first thing that we are going to do is we are going to deal with the continuous outcome. When we have a continuous outcome, what are the things that we generally do? And in this case, what we are going to do, I have basically saved the dataset, the analytic dataset that I have created in the previous chapter, and I'm just basically calling the dataset. And what I'm going to do is I'm going to predict this length of outcome variable that I have, length of state variable that I have using all of these other variables. So what are these other variables? As I said, I have 50 covariates in this data set, right? Within these 50 covariates, I have disease category, cancer, cardiovascular disease, and all that. So there are many variables that were given in that particular data set. And I'm basically trying to use all of these data sets or variables to predict my outcome length of stay, right? Okay. So as you have mentioned that if you have a continuous outcome variable, you need to use a linear model. So in this particular scenario, since we have many covariates, so we are going to use multiple linear regression to fit this. And forgetting about anything about machine learning and all that for now, whenever you have a continuous variable and you are using regression to utilize all of these other covariates to predict your outcome, you are basically building a prediction model, right? So let us see how we are going to do that. So at first, what I have done is I have defined the name of the variable. So in here, what I have done is that other than the length of stay and depth, all of the variables, all of the other covariates that I have, I'm basically incorporating them into one vector. It's called the baseline vars, right? And then once I have the baseline vars, what I'm going to do basically is I am going to create a formula out of it. The length of stay is going to be the outcome variable in that case, and then I have the baseline variables that are going to be on the right-hand side of the equation. So I'm using all of the baseline covariates to predict my length of stay in this particular example, right? And then what I'm going to do is I'm going to use the LM function. So whenever you have outcome being continuous, Gaussian regression or linear model, whatever you call it, you are just going to use the linear model and you are going to use the ops data, which is basically our analytic data, to create our linear model. And then you can use the publish package. So you can obviously get a summary of the fit from basic R, that's not a problem. But you can use the publish package to get a nice summary of the fit that you have. Say, for example, when you have the formula, look at here, the formula that I have written using the test function over there, that formula actually looks like this, that length of stay is the outcome, and all of these variables are basically the plus. There are no interaction term, there are no polynomial term. I'm basically keeping it in a very simplistic level, right? And once I have done that, and I have used the publish package to extract the fit looks like this. So basically, you can see I have an intercept term, of course, and then I have the disease category, and within the disease category, I have some of the variables. And associated with all of these variables or labels, I am getting the coefficients associated with each of these levels, right? Say, for example, I have this cardiovascular event, and this is a binary variable, and this has a event versus no event scenario. And the 0 is associated with no event, and 1 is associated with event, whether the person had cardiovascular event. And then I have a coefficient associated with the cardiovascular event, and that is going to be 0.7. This is a regression coefficient, by the way. I have not transformed this to any other thing. This is a regression coefficient. And then I have the confidence interval out of that regression coefficient, whether this 0.7, whether this is a zero slope or not. And then I have the p-values associated with it. And that is happening with all of these covariates in this particular regression. When you have a prediction in your goal, so you are thinking that I want to predict the length of stay to the best of my ability. You don't really care what is the interpretation of this 0.7, right? So this is basically a nuisance parameter that you are getting out of the model. All you really need is the prediction that you get out of this model, right? So the exact value of this or the interpretation of this when you are building the prediction model does not really make a lot of sense, right? So why would you even check this regression, the fit of this regression? Sometimes what happens is that if you have two variables that are giving you very similar information about the outcome, they are sometimes highly correlated. When they are correlated, there is the level of correlation, right? The level of correlation could be low, correlation could be high. Sometimes if the correlation level is very high, to the extent that from one variable you can linearly predict what is going to be the value of the other variable, sometimes there can be multi-collinearity issue. When this happens, that your data has two variables that are collinear, then having those two variables in your prediction model will mess up your regression in a way that the confidence interval that you will get will be very wide, right? So as a diagnostic reason, you would want to check the regression, even though you do not care about this particular value, like whether this is minus 1.8 or not, you don't really care too much about it. But if this value is like 18,000, then you certainly know there is something wrong going on, right? So you go back to the modeling and try to figure out what is the problem with it. Or you can see this confidence interval that is very wide. By wide, what do I mean? Like the width is 3? No, like 3,000 or something very big. That when you see it, you obviously understand there is something wrong going on, right? And obviously there are some other tools that you can use, some sort of VIF function, variance inflation function that you can use to assess whether there is some variance inflation going on or not. But generally speaking, the message that I'm trying to say is that I do not care about the interpretation of this. All I care is the diagnostic, whether the regression diagnostics are good or not. There are some interesting packages within R that can give you some interesting diagnostic thoughts in terms of checking the performance measures, like how good my regression is doing in predicting the outcome. Some of those measures you already know from your basic stat courses, like R square, adjusted R square, and things like that, right? I know that there are packages that will enable you to directly get the adjusted R square, and all that, but I just wanted to want you to show or know at least how we calculate those R square or adjusted R square, just so that you are aware. So in that, what we are basically doing is that basically we are converting our regression into a or the data that we have into a model, into a design matrix. So think about how many covariates we had. We had exactly 50 covariates, not more, not less, right? Exactly 50 covariates. And if we include the intercept term, it will be 51 covariates, sorry, 51 parameters, right? But quite not that, because we have some of the variables that are dummy variables, right? Remember in the regression, we had, say, for example, income variable. And income variable had some of the different levels, right? Under 11K and over 50K and in between. So in here, I have 4 different levels within income. So they all will be associated with at least one parameter, right? -1, because there will be only one, that will be the reference category. So you will also have to have a general understanding of how many parameters you are going to get out of that regression. And to be able to understand how many columns you have and to convert them into a regression format, you need to know the design matrix. In that design matrix, you will have something like this. Say, for example, let us take the income category. See, remember there was one income category that was the reference category that is not here even anymore. All you have is the 1, 2, 3 level of income that you have. Originally, we have 4 level, right? So when you have a multi-category variable, say, for example, income had multi-categories, What this design matrix is doing, it is converting that one column variable into this 3-column variable now, right? How did I come up with this 3? Because I had 4 categories minus 4 minus 1 and 3 categories, and 3 of these categories or the columns will basically look like this, or like binary variables. But if you already have a binary variable, there is nothing to change. There is the same variable that you are going to get. Okay. So in this, what we can basically do, when we create the design matrix, we can basically get how many columns we have in that design matrix, and that will give our P. And P is basically the number of parameters that we are going to get. So how many parameters? One will be intercept, and everything else will be the slopes associated with each of these columns of the design matrix, right? Is it clear that there is a difference between the original data and the design matrix? Design matrix is obviously going to have at least the same or more columns, depending on how many categorical variables you have in the data set. For continuous variable, this is not going to do that. Continuous variable, it is going to remain the same. Okay, so you have your P, and what is your N then? N is the number of rows in the data set, how many subjects were associated with that. Once you have your P and N, then rest is easy. You are you are basically doing is that you have this length of stay as your outcome variable, and then you can predict from your feed variable that you got out of your linear model. And then you can predict, and you can get the summary of the prediction, and you can get the summary of your original outcome. See, if you look at the original summary, the length of stay stayed between 2 to 394 days. When you predict using the model, you could stay minus 32 days in the hospital. What does that mean? I don't know. So, and also the maximum is 42, whereas the maximum was more close to 400 days over there. So right off the bat, you already know the prediction is probably not that good, right? So we will try to get an understanding of how good is the prediction. And using the R-square, we are trying to get a general sense. And this is basically a plot to show the relationship between the predicted and the observed. If this was a good plot or the ideal plot, we would expect something a 45-degree angle. But this is not that. What I have done is basically I have used that kitchen sink model to predict. So the kitchen sink model was in this fit1 object. Within this fit1 object, I had that linear model that I had saved, right? And when I'm using the predict function, all I'm doing is I'm using this fit1 object to predict. So I'm not using the length of stay variable anymore. All I'm using is the model, the baseline, the model in the right-hand side, to predict what should be my y, right? And once I do that, I get these predictions. So of course, we now have seen a model, a prediction, and we kind of know that this model is not really working that well, but we want to be able to measure how good is the prediction, right? And to be able to do that, there are some measures of prediction error. And I'm just going to measure those prediction errors to figure out how good is the prediction. All right, so why do we need this prediction error? So basically speaking, generally speaking, you will see that if you have, say for example, if you start with one variable to predict your outcome, you will have certain amount of predictive ability. The more variables that you add, the more predictive ability you will have in your model, generally speaking, right? Because you are certainly putting more information to predict your work. But the problem begins when you start adding unimportant or noisy variables that had nothing to do with the prediction of your outcome, right? So the more of this noisy variable that you add, the more of these things will happen where the predictions will not be as good, right? And so there has to be a variance bias trade-off. What that means is that the more noise variable that you add, the more noise it will add in your prediction. So you certainly would want to make use of the full data access that you have, but sometimes this full data, much of it is not really useful in predicting your outcome. So there has to be a penalty for pushing like unimportant variables in your model, right? So that is why we have these measures like adjusted R-square or something like that. So R-square is something that is basically a mathematical formula that calculates the total variation and the variation of the difference, and then takes the subtraction. This is just a formula that I copy pasted from Wikipedia. So there is nothing new that I'm showing here. This is if you are familiar with linear regression, R-square usually is in the same chapters of the book. So in the R-square formula, what we are basically doing is basically we are having our observed y, which is what? The length of state. We have our predicted y1, which is what? The predicted value that we get from the model. We're basically subtracting them. We are taking square of them, and then we are summing up all of this, right? And that will basically give me the sum square of error. And that makes sense because I'm just subtracting between what is observed and what is it that we have predicted. And the difference is going to be the error, right? Okay. And then what we are doing here, we are also calculating the sum of square of the total. So how do we calculate that? We just have our observed value, and we just have the mean observed value. So this is the length of outcome, and this is the mean of length of outcome, right? This has nothing to do with the prediction, by the way. So we can all calculate that when we have access to the data. And we just calculate this sum square, and we calculate this as sum square of total, and this is the sum square of error. And all we are doing is basically we're calculating the portion of error within the total, and we are saying 1 minus that. So how much of the model is explaining the total variability? That is all we are doing here. And in here, we are getting a number 0.07 or something like that. So the range of in an ideal setting, if you have perfect prediction, so all of the observed y values and all of the predicted values are exactly the same. There is no deviation. Then if you calculate your R-square, your R-square will be, anybody can guess? 1, right? And so that's the best case scenario that we can have, right? And since this is sum of square, because we are using sum of squares here, right? So no values can be negative, right? So the minimal that we can have in here is 0, theoretically speaking. And in the range of 0 to 1, what do you think about this value? Really bad, right? And that kind of confirms our observation about the difference between the observed and the outcome. All right, and within the caret package, by the way, you can, like, if you do not want to calculate all of this by hand, you simply can calculate this, supply this predicted and observed value, and caret package will calculate the R-square value, which will be the same. Okay. The other object that we can use to do our prediction accuracy, this is called the root mean squared error. Anybody familiar with analysis of variance in here? Okay, so this is slightly a different version of regression that statisticians sometimes use. All I'm trying to say here is that there is a different formulation. I don't want you to get bored with the formulas or anything like that. All I'm saying is that there is a framework, and using that framework, we can use that framework to calculate the sum square of error in a slightly different way. And that can also give you some understanding of the how to measure the prediction error. And in this, the 0 can be the minimum, and the maximum can be infinite. So the range is slightly different here than the R-square. And you can see that 24 is the value that we are getting out of a root mean squared error. The problem with root mean squared error is that we do not know what is the upper bound, like it's infinite, right? For R square, it is very easy. We know that R square 1 is the upper bound, so we know exactly where in the range our R square is belonging. Root mean square error does not have that advantage. But when you are comparing two different models, then if one model is giving 24 and another model is giving 30, then you can compare. So that's the purpose of root mean squared error. The root mean squared error, what you have is that you are using the n and p both, right? But in the R square calculation, when you are using more and more covariates, you are just rewarding the model by assigning more R square values, right? So adjusted R square is basically a correction to that. Whenever you have an R square value and you are adding more and more unnecessary covariates, it will penalize your R square value, right? So that's what the adjusted R square is. And when you calculate the adjusted R square, you are getting even lower adjusted R square value, right? So basically, people use these three measures when your outcome is continuous to measure the performance of your model. And obviously, all of these have their own advantages and disadvantages. All of these are not giving you the exact same information. But when you calculate all of this, you basically get a very general understanding of what is going on. One thing I should tell you is that adjusted R square can sometimes be negative. So you have to be slightly careful about the interpretation of adjusted R square. That is why people, even though they calculate adjusted R square, they sometimes calculate R square as well, to get a general feeling of what, between 0 and 1, what is your R square.
Can it be negative because you could penalize so much by having too many covariates?
Yes, yes, basically for that. Okay, so in this particular chapter, one of the last things that I want to cover is the overfitting and optimism. What that basically means is that when you are using the same data to build your model and to predict your model, same data, nothing changed, the model is going to show that, the performance measures are going to state that your model is performing better. But as soon as you use one data to build your model and use another data, maybe future data, to predict what is going to happen, the R square or adjusted R squares are going to be lower, right? And that is something we called the optimism problem, that if you are using the same data to build your model and calculate the performance measures, you are certainly going to get more optimistic statement or results out of that. Right? So basically, the consequence of optimism is that the overestimation of the effect of the predictors and the reduction of the model performance in a newer observation. So once you have built your model using the data of 2020, and you are then using the data of 2021 to predict, then the R-squares values are going to go down, generally speaking. And that is one consequence. And to remedy that problem, there are some techniques that are available. If you are going to use, if you just have access to one data and you have nothing you can do to bring new data, and that is usually the case in many scenarios, then all you can do is internal validation, right? And internal validation is very simple idea, is that within the internal validation, there are some of the techniques. The first technique is the sample splitting. I'm going to spend some time in explaining that in the next section. The slightly modified version is known as the cross validation, and bootstrap is basically a slightly different version where you do repeated sampling and all that. I'm going to explain that in the next segment. But if you were in a situation that you were able to collect some external data, say for example, for British Columbia, you create one model for predicting the length of stay. And then you also have some collaborators maybe in Alberta, and they can be collect some other data or on the length of stay, and then you can use British Columbia model to predict the Alberta data. That will probably give you some understanding of how good is your model. So that helps your generalizability of your model. The model is no good if you cannot generalize, because think about it. Why do you build prediction model? Prediction model is for prediction, right? If you already have the data, that's not prediction. You already know what is your Y, what is your outcome, what is your length of stay. So prediction models are built for prediction so that they work. So you are hypothesizing that this model will work when you have new data. And if the new data comes and your R-square slightly, like drastically goes down, your model is no good, right? That's why the generalizability component is very important when you are building the prediction model.